How does this work?
Yeah, those big buttons.
Or is that
Yeah, there.
You did it right? Okay.
Okay, what do you need? These ones right here.
Thank you. Okay, good. So, great. So it's really great to have Manfred here, talking about Fall Leader with Dropout Perturbations and a special week for Manfred.
Yeah, special week, right. Okay, so I talk about dropout perturbations, and this is something we discovered this independently, and later on we noticed we were doing dropout. So dropout is usually known neural network context, some kind of a layered neural net, and you feed your inputs, computation goes forwards, and then they're trained with stochastic gradient descent, and your gradients are propagated backwards with backprop. Now, the dropout training is you randomly throw out nodes with probability 1/2. You have a remaining network, and you just do your training based on that network. There's many variations of it, and we do a variation of it for just one single neuron. And in practice, this works better in some contexts, but of course, everything is changing all the time in the world of heuristics. Some people tell me that dropout is not so important anymore, but we found something that works for a single neuron. It's dropout-like at least, and it has these interesting properties, this dropout noise. Okay, and it was why does it work, and so forth. But we only do it for a single neuron and linear loss. So now I explained to you the expert advice setting, which is the basic setting, one of the basic settings in the cold community, for which we have very tight bounds. And then we applied dropout noise, and we had some advantages. And that kind of noise is independently interesting. A lot of people here in the room have worked on various noises. So expert setting is something like you have a bunch of experts, they predict something. It's rain, it's not going to rain. Then you have a master algorithm that combines the prediction, predicts 0, because there was more zeros maybe. Then you get a true label and you get a loss. There was a disagreement. Next day, the experts predict again. The master prediction might be a 1 now, get the label, and you have a loss. You have no loss because they agreed. In general, you have some predictions from the experts. Prediction of the master, true label, absolute loss. It's a very simple thing. Okay?
Excuse me.
Yes?
Maybe you're just saying this, but yeah, you can't predict a probability?
You can predict the number in 0 and 1.
Okay.
Yeah, that's what it's usually, yes. But I'm going to abstract this away in a moment. So here, yes, see, so these are in between 0 and 1. And the y hat is between 0 and 1. The true label might be binary. Yeah, there's many versions of this. Good. So the idea is that the master algorithm takes a weighted combinations of the predictions of the experts. Very simple model. So the master algorithm predicts with w.x, and wi is the belief in expert I in some sense. And now notice that in this particular case, when the label is 0 or 1, the loss actually linearizes. In other words, because this is binary, it linearizes. Okay? So now we come to a very simple linear model. So this is the first one with absolute loss, where you get an advice vector, you predict with a weighted combination, you get the true label, the expert get this component-wise loss, and then this is the loss of the master, which is a weighted combination. This can be abstracted away to what we call in machine learning the hedge setting, where instead of feeding inputs, you can view it as the following. You view as experts getting loss vectors at the end of each trial that are numbers between 0 and 1. And then the model is very simple, and this is going to be my basic model. So this one you have to understand. You have a weight vector, which is your parameter. You get a loss vector at the end of the trial. And then the expert incurs this individual loss. This is a number between 0 and 1. And then the master algorithm is charged by the weighted loss, by W.L. So what your objective is, you have these arms and they feed you losses. You are supposed to put all your weight on the good guys that have no losses, have very little losses, right? And you want to do this in online fashion. You have the game? Yeah? And this has this in some sense as a special case, therefore this justifies this abstraction. That's the idea. Okay. So when you predict with a weight vector, the weight vector is a probability vector. Instead of predicting with a probability vector, you might as well pick an expert at random and pick with that one. That's interchangeable. Yes?
I'm sort of slow down, but I guess something doesn't make sense to me.
Yes?
So is this a proper scoring rule?
Is it a proper scoring rule? This is not a proper scoring
That's
rule.
what I thought. So why does it make sense to use an improper scoring rule? To do something that isn't a proper scoring rule?
We don't use this by itself. We just judged by that. We judged by these linear losses, but we predict with proper scoring rules because we add regularizations. It's a very good question. We'll get to that, okay? The properness is sort of introduced by the noise, okay? Good. So now, as I said, the game is you have a probability vector. You might predict an expert. You might choose an expert at random from that probability vector. You get your loss vector. Each expert has a loss between 0 and 1. Then the master is charged by W.L, which is the expected loss. If you picked it at random, then your loss is the expert you picked times LT, so it would be LT IT, but in expectation, this is the same. So I'm going to switch back and forth between these things. Right? This is a basic trick. There's nothing deep about it. Okay, good. And then you update your weight vector, because this is the game. Okay, good. The weights over here are implicit. Okay, good. What is our criterion for success? It's a regret. So I really have a very basic problem. We do this iterative game. This is the loss of the expected loss of the master algorithm. And what do I compare against? The best loss in hindsight. So this is my notation. I looked at the loss vector. I sum up all the losses in component I. This is the total loss of expert I. I'm going for the best. This is the loss of the master algorithm at time t, and I sum over whole trials. I look at that gap. That's called the regret. You with me? This is a totally ridiculous loss in some sense because it's all linear, right? So it's no properness of anything. But we will predict with proper things somehow by adding noise. So it's a very slippery thing because it's linear, right? So it should be very suspicious. But we can prove bounds. In the cold community, there's a huge family of algorithms. And we figured out that Dropout works and it has some additional magic. It's really cute. So this dropout noise is very cute. So here are the algorithms. Okay, again now, I don't put predictions down for the experts, I put losses down, right? So this is my day 1, here were the losses, day 2 were the losses, day t minus 1 were the losses. So what I do is, I have sort of a sufficient statistic, I add up all the losses so far. So this is my losses, right? Okay, that's one way, that's one thing. And now I can do follow the leader. Follow the leader says, predict with the expert that have the smallest loss. Right? So I would predict with these two, 50-50. You see? Let's follow the leader. Right? A deterministic follow the leader would actually predict with a particular guy of the best. That's worse. But randomized is better, but you predict with the best. Okay, so that's follow the leader. I'm trying to, in this talk about things you could teach in a machine learning class, right? Basic ideas. Okay, good. So, another one, Sanjoy is here, I think, is you have additive noise. So you take this total losses, you add additive noise tuned by some kind of a stretch factor. Okay, let's follow the perturbed leader. You understand? Follow the perturbed leader. Okay. And a third one is soft min. Soft min would be you take these total losses, you put them in an exponent with a negative side, scale factor, and normalize. That means it puts weights on the guys of small loss, but in a continuous fashion, soft min. Yeah? So if you let learning rate go to infinity, this would be equal to that. And it turns out you will see that this algorithm you can simulate with this algorithm, as you will see in a moment, or vice versa. What's dropout? It's not even politics. Okay, good. So now what's dropout? Dropout is you don't add noise. What you do is you cross out the ones with uniform probability. The zeros, if you cross out, doesn't make a difference. So everything is dropped with probability a half. You see? You add your tally, and then you go with the leader. So in this case, you would go with this guy. You see?
Deterministically now?
Well, in this particular case, because there was only 1 0.
No, but
No.
the randomization
Yes,
is only
yes.
on the crossing.
Yes, it's always there's lots of randomness involved because you cross randomly and then you pick amongst the leaders uniformly. Okay? Good. So pictorially what happens is I'm not in the neural network case. I'm in the very naive small case, single neuron. One neuron, and now I drop with the probability 1/2. You see? And so it's sort of, and then I take the leader, follow the leader, I go with the best. Very simple noise. So some people, I showed this to Hinton in this particular context, and he says, yeah, it's multiplicative noise. Because you, instead of adding to the losses something, right? People have actually added, this is a Bernoulli random variable. You can take your total losses and add Bernoulli random variables for each trial. Has certain problems. Here what you do is you do multiplicative noise. And it turns out that multiplicative noise, where you wipe out, has advantages. And that's what this talk is about. Okay, does everybody understand this? Yes. Go ahead.
So do you repeat the cross-outs, the dropouts every iteration independently?
Yes, independently. And this is really...
So you might retake something you dropped out earlier?
No. So you get each time a new row. You have the past row. Each time you get a new row, you drop out, you do your predictions, and then at the end of the trial, you drop and you recompute your tallies. And each time you follow the leader of your...
Whatever was dropped forever.
Yes. Really stupid. Why would you drop this valuable data, right? Why would you? Of course, you want to have robustness, and this is the whole thing. And in this particular context, it does the optimal thing if you drop. Bizarre. You would not want to drop. I mean, additive noise makes a little bit of sense, but you just add noise variables. Okay, you blur, but you keep all the information, maybe. But here you drop all your valuable data. Why would you do that? Yeah? Now, there is an alternate version I will just get to, follow the skipping leader, which is where we are, that we wanted to prove works, where you would take the whole row and drop it with probability 1/2. I'll get back to that one. That would have many advantages, and we were after that. We never proved anything about it, and finally somebody showed us a counterexample. It doesn't work in our worst case criteria. So we needed the independence on the components. Okay? So it's a study of what kind of noise is good. Okay, and I show you the proof techniques, and they were kind of interesting. So how good? Well, we know that in this case, the best algorithm, the best regret you can achieve is this, upper and lower bounds. It's log of the number of experts, and then a square root term with and this is the loss of the best. See? So the loss of the best appears in the bound. The loss of the best expert. Do you understand what I mean? So this is the regret. You can have algorithms and Dropout is going to be one of them, that achieves this optimum regret. The algorithm just runs along, and you can always guarantee this bound. Yeah? Okay. Good. Now, let me talk about the algorithms a little bit. Very interesting. So follow the leader is bad for many reasons, because you somehow, the adversary knows too much what you're doing and it can fool you. And I will give you hints of that in a moment to get your flavor of how it works. Now, follow the perturb leader, randomness, the adversary doesn't know what you're doing because he doesn't know your randomness, right? That's what we assume. And this works well, it gets the optimum bound, but you need to tune the learning rate as a function of L star. If you have a lot of noise, if the loss of the best is very high, then you don't want to do a lot of updates. If your loss of the best is very low, you want to have a large ADA. And you need to know what regime you are in to get the good bounds. Good? Now, Dropout requires no tuning. That's its first feat. It's totally trivial. It's not additive noise, it's multiplicative noise, and it achieves this bound. Okay, constants always ignored. So it gets the optimum regret, and, which is very cute, and that's why I'm in this workshop, it also is good in the benevolent data case. When your data is IID, okay? When your data is IID and there's sort of a gap between the first and the second, then it even figures it's optimal also. It has the log n regret. So it's good in the average, in the IID case, when your data is not worst case, and it's good in the worst case. So it has these two features. And it's a trivial noise. And the noise is interesting in itself. It's just throw data away, right? Okay? And this could have many implications because, look, this problem with the dot loss and this simple hedge setting, which comes from the regularization algorithm, it's a paradigmic thing that is used all over. You could do logistic regression and then drop your gradients. Set your gradients to 0 uniformly with probability a half, and maybe, again, there's no tuning. I don't know. Open. So we are theoreticians, we work bottom up and prove things about very simple things, and we proved that Dropout in this particular case works, and we had a lot of fun. Okay. So there is many fancy algorithms that achieve this, but they're very complex. They have potentials, they have, they have versions of the Hedge algorithm with fancier things in the exponent and so forth. Very beautiful work. Rob Shapir's a group, Tim van Erven, and also Joachim Freund at San Diego did work on Brown Boost. Very beautiful algorithms, but significantly more complicated than Dropout, and this Dropout is interesting in its own right, I think. Okay, now how did we run into this? Yes?
A little confused why you do Dropout instead of free. Like you didn't change 0 to 1, you just change 1 to 0.
That would be a little, I would be nervous about that because you could have lots of zeros. We show in our proof that the hard case for this setup is when this row has only single ones. So when you do your flipping, it would introduce a lot of stuff. Maybe with flipping not with probability 50-50, with a tuned probability, who knows? I mean, anything is possible. We don't know. Yes?
You said you ignored constants. Do you know the constants or like?
Yes, we know constants. Yes. There's pretty parts of the proof that I talk about, and then there's very complicated, ugly computations, right? So, yeah, there is constants. Not high though. Not all in the order of 4 or 5, right? Not hundreds. I'm not hiding something. Okay? And you can run these algorithms and they work well. I'm not hiding anything. So it's not the theoretical computer science talk where I'm hiding something. Okay. What? There's no O. It's not fair to put an O there. It's small constants.
Oh, sorry.
I have bad eyes.
Curious real quick.
the L star in there, can't you get like a tighter regret bound where it's replaced with like some of like losses of the best expert like squared? Isn't when
You can get better bounds. There's better bounds where you have quadratic terms in here.
Yeah.
Yes, but they require fancier algorithms. And I want to talk about something simple here.
Sure. Okay. So when you say optimal worst case, you just mean that like that one gives you the optimal dependence on like T and N.
On L star. On L star. Not fancier versions of expressions here.
That depend on the individual. Okay. I see.
Yeah.
Sure.
Yes. So I'm doing something. I'm not sure whether our algorithm actually. It's essentially, he's hinting at algorithms that don't just take the total loss into account, but also some variance type thing. Okay? And this is the question whether Dropout has also good properties when the variance is small of the best expert. That's beautiful research topic. Yes?
I was wondering about variance as well.
Yes.
I was wondering, have you thought about a situation where you replicate each data point and do dropout many times randomly on it? I wonder if that would have different conversion.
The kind of thing that I have tried with variance is various algorithms that do the following. You look at the leader set and you only do perturbations there. You only drop those. And we have a bunch of algorithms and we have huge simulations. The damn thing, we can't prove anything about them. So unfortunately, I'm in a theory community and I cannot publish it. If I would be in an experimental community, I would just publish things on a big amount of data and I would have a beautiful paper, but I can't. I'm being facetious. Good practical work is very, very tricky, and good experimental papers are very tricky. So I'm just being funny.
So just another variation, another complication for possibly no reason. So in the limit, you're getting a normal distribution on your tallies?
Yes.
So how about multiplying your payoff, your loss by a normal distribution, and then adding those?
Yes, that would be similar. Yes, that would be smooth. Yes.
So.
Yes, would work.
Okay.
Or versions of that would work. But sometimes you have to watch out. I did binary losses, and if you have epsilon losses, you can do a little trick. You sort of give everybody a small amount of epsilon loss, and then you figure out where the leader is, and then you hit it. And in the worst case, you need to binarize your problem. There was a little detail. There's subtleties. Anyway, but let me give you a little bit of a flavor how this works. Okay, so it has good in the worst case, and there's fancy algorithms. Okay, good. And they have other advantages, variance bound. So how did we get into this? We didn't want to analyze a hedge setting at all. We were after a matrix problem. Well, it turns out there's a beautiful matrix generalization of these kind of softmax algorithms. The loss vectors become loss matrices. Here the losses between 0 and 1. These are positive matrices with eigenvalues between 0 and 1. This will go by a little bit, but you get the flavor, okay? So probability distributions on experts become density matrices. Density matrices are, the eigenvalues are the probabilities, and then you have an eigensystem as well. That's quantum physics kind of probability distributions. Then this is the Hedge algorithm, soft min. It's also used in boosting in many, many contexts whenever you have entropy regularization. And then there's a matrix hedge version where you take the total of all these loss matrices and you matrix exponentiate them, normalize, and that gives you a density matrix. And this was used to learn principal component analysis, because there you take care of a subspace. And this kind of takes care of this takes care of the best experts, and this of the best subspace in some sense. All of these algorithms take order n cubed per update. One of the biggest problems in this online community is get this down to n squared. Well, if you could do some kind of a dropout where the dropping is very simple, where you drop the whole matrices, right? You would add them up and just look for the best eigenvalue. You could get it down to n squared. So we are obsessed with getting it down to n squared. We haven't been able to make our proofs go through. And this gets to follow the skipping leader. Follow the skipping leader would be, we have a beautiful name, but no paper. Follow the skipping leader is like you drop the whole row with probability a half, right? That's the natural thing to do, not this independence thing. Or in the matrix case, it would be you drop each loss matrix that you come with probability half. You set it to 0, and then you add them up, and you do a minimum eigenvalue computation, something like that. Yes, that would get it down to n squared. But it's kind of like an online bagging type thing. But then Gerglinoy showed us a counterexample that it doesn't work. If you want, I show you at the end. Very beautiful. Okay, so our proof techniques break down. We were very upset about it. So we settled for writing about the Hedge algorithm again. So this was Lugosi and Noy that gave us this counterexample. Okay, so how does this all relate? Where does Hedge algorithm come? Well, Hedge algorithm is you regularize with a gradient descent, and that makes it somewhat proper. That's how you avoid the slippiness of the linear loss. It turns out, this is kind of an interesting fact, that if you do additive noise with log exponential, sometimes called a Gumbel distribution, then you get the Hedge algorithm. So this follow the leader with additive noise can simulate the Hedge algorithm. Okay? That was kind of a funny exercise that we had to do. It was a couple of NIPs back. There was many papers on this. But Dropout, I don't know what the regularization is. There's many, many papers that try to figure out what kind of regularization is Dropout, and it's a mess. It's not a mess. It's very complicated, and the answer is not clear. But in this particular single neuron case, it does something good. Okay, so proof methods. Okay, good. Now, let's say, and I had discussions with Avram about this kind of things before. I'll show you. So follow the leader. Follow the leader is you just predict with one guy who's the best. Let's assume we predict deterministically. Then the adversary knows what you do, and he give you a unit loss. After t trials, you get 2 units of loss. But there's one guy which has t over n. You have an expert t over n loss. So your regret is huge. Your regret is going to be roughly a factor of n times L star, and it should be square root of L star log n. So that's very bad, because the adversary can fool you, right? The adversary can hit you just what you predict. So if you hedge your bets by predicting uniformly amongst the best, you're already much better. And this was an algorithm that you showed me years ago. So this was the optimum. So now you do FL with random dice. So what you do is, you assume there's an expert with no loss. And you get your loss vectors, and you wipe out the ones that have loss until you run out of experts. And then you start with a new set. And if you do that per sweep, per phase, you can make at most log n loss. And you can see that by doing the following. If the adversary gives you 1 unit, if only one expert has a unit loss, and you predict uniformly, you get 1 over n loss, 1 over n expected loss, and then afterwards you have n minus 1 expected experts left, and it's this harmonic sum. So per phase you can show you can make it most log n loss. So in total, it's L star log n regret. So this is a huge jump from linear to this by using randomness. But it's still not the square root. Yeah? To get to this, you need to do other tricks. And you do Dropout, for instance. So what we prove is, we prove that our Dropout algorithm has the following very simple property. The proof technique is interesting in its own right. Okay, so if your loss vector looks like this, so then you could say it's in the adversary's advantage to take that loss vector apart, put it into 3 trials, and give you 1 unit of loss each time. You understand? It makes you can prove that it makes you incur more loss. Follow the leader also has that property. Follow the leader with breaking ties uniformly also has the unit rule as its worst case. So we call that the unit rule. I discovered this first with papers with Jake Abernethy. And yeah, so that's a beautiful thing. That simplifies things. So you only have to concern yourself with the adversary playing units. And now we're going to say, we're going to prove that we can assume the worst case happens when the adversary places them in a particular order, the units. We'll see that in a moment. Okay, so this is the unit rule. Okay, so now what happens is the following. As if you have a particular, assume you're done with your whole experiment, and expert 1 got 9 units of loss, 8 units of loss. This is the loss profile that you have at the end. Now, it was played by playing units. So each of them has a number associated with. Maybe this one is played first, second, third, fourth, fifth, sixth, seventh. You know, you walked through those units from left to right in a particular order. And then we figured out which order is worst. Which is best for the adversary, which is worst for the algorithm. And it turns out you essentially have to take them layer by layer. Because we showed that if you take this one before this one, then by swapping you occur more loss. Do you get the idea? So the worst case pattern is always this. Sweeps. Nice sweeps. And then here's your loss of the best. And then you sweep some more. That's the worst case pattern. So that's the only thing you have to analyze. That simplifies the proof. There's still an ugly part left. But let me now tell you how much you pay per sweep. Do you remember that follow the leader paid log n per sweep? So we have to get rid of that log n, right? And we do.
The algorithm can't take advantage of a sweeping adversary? Like if the algorithm knows that...
This is only worst case for that algorithm.
It's worst case for this algorithm. Yeah. Yeah, so if I have a sweep like this, I would stay uniform. I understand. If the worst case pattern is this, then I would stay uniform. I predict uniform with an expert. I would get 1 unit of loss each time. And then at this point, I would finish. I would notice that there is one guy that doesn't have any more loss, so I would take L star plus 1 loss. But that's cheating. Against that algorithm, I can fool it in a different way. Yes? But you get into the spirit. Good. So we're good. So assume you have S leaders at this point, right? You have the history already dropped out things. You have S leaders. And now you do a sweep. All the ones that are non-leaders you can ignore. Now I'm asking you, how much loss do you get per sweep? And here's the deep insight. And it's very pretty, and we just were fascinated by this. Okay, so I showed you already that if you follow the leader, which is the algorithm that is intuitively obvious, if you picked a random one, then on the first trial you make 1 over S loss. Then the number of experts goes down. You picked another random one, n S minus 1. You sum this up, log S. Bad, because if you have n leaders in the worst case, you pay log n per sweep. Huge. Too big. What does Dropout do? I claim Dropout spends constant loss on this pattern. Constant. And it's totally bizarre. So what it does, and first I show you the wrong proof, okay? So maybe I shouldn't tell you. Okay, so you do 1 over S. Now what happens is you drop the leader with probability 1/2. So afterwards you have only 1 over S minus 1/2 leaders. Roughly. Then you have 1 over S minus 2/2 leaders, right? And afterwards you have 1 over S minus 1 over 1/2. So basically you have this thing. Now, if you add this up, it's a constant. Because it's the tail of the harmonic. You know, this harmonic sum is huge right around here. This is where most of its log n loss is. Over here it's a constant. Yeah? So you can rescale it and so forth, and you get 2 log n. Now I cheated a little bit. I used Jensen's inequality the wrong way. But you can compute this kind of calculation, this dropout on the sweep, precisely with a recurrence. My co-author Wojciech Kodwowski, genius. And then you show that it's constant loss per sweep. It's bizarre, right? So again, what's happening? Follow the leader. It's something very basic. Follow the leader has loss. Does everybody understand that? 1 over S minus 1 down to 1. And this is the harmonic series. It is log n, log S. Yeah? Now, if I do dropout, then my number of leaders drops down slower. Because you see, if I pick a random expert, once in a while, if I would put stuff on something that had its unit already in the sweep, and that helps me, or something like that. So I go down only slower. I go down slower with this sum, and that sum is, this term goes like this. It looks like this. It goes up, and over here is all the log n cost. The total but initially these things are so small that they sum up to 2 log 2.
But you're still a constant factor larger than
I'm going to, okay, so the picture is, here I never can make more than a constant loss. Now, if I have L star of this, it would be a constant sum L star, too big. So, but it turns out we should now show, and this is the ugly part, and we learned that from Gerglinoy and Lugosi, that with high probability, after a while, you have only one guy, one leader. And in that case, we treat that as a special case, and we win. So when we use their theorem to show that most of the time, it's actually 1. And if it's 1, we're perfect. And when it's not bigger than 1, we just plug in a constant. You see? So it's you got the gist, of course, because he teaches this stuff. So the simplest case is, again, let's say we have 0, no noise. What's going on? What's going on? If you have no noise, you follow the leader with uniform ties broken. Again, you have that log n cost, which is optimal. You can prove it's optimal. The algorithm, the dropout, pays constant. We know that the sweeping is the best one. It pays constant per sweep, but each time reduces the number of expert I have, and it takes log n sweep, and you can show it's 2 log n. Slightly worse, but totally different. It arrives at the unique expert totally differently because it drops things. It's very beautiful. Okay, so focus on the first L sweeps. Most of the time, the number of leaders is small, and then this is more complicated. Anyway, if you tune Hedge based on the optimum learning rate, it looks like this. It takes constant for these kind of things, and then it flattens out. Ours goes up like this, and then flattens out at the end. This is the case where L star happens. Anyway, the bounds are optimal. Is kind of pretty. Okay. So we're not interested in proving things for single neurons. Yes, we also want to do more complicated things, but we don't know. The unit rule breaks down. Our proof techniques break down. We have, it's insane. We're just lucky to find this little morsel. But then, of course, the correlates are supposed to be proved by the students or the other people. But it's much harder. The key thing is you always have to be first and prove the first beautiful result, right? And we were lucky here. So the matrix case is still open. Maybe there's a trick, we don't know. If you, of course, go in there and eigendecompose each loss vector and do all kinds of things, then maybe you can do it, but I don't know. So we want to get this to order n squared, and the really annoying thing is there is another algorithm called Oja's algorithm, which runs in order n for PCA, for instance. And we don't know whether that works in the worst case. So there's layers of open problems for us. Very, very challenging problems. I've worked with people. My research is always, it's a sequence of obsessions. This is one of my obsessions, cracking these matrix problems. I have not succeeded. Okay, now this is a new kind of noise, right? And it has these properties of some, you try to use it for other things. Try to use it for convex losses. Drop gradients by 50%. Do logistic regression. Drop gradients with probability a half. Does it self-tune? Interesting problem, right? Don't know. And then, of course, the dropout for neural nets. Prove something about them, instead of just heuristics. So, and also this additive noise is used a lot for making things private, you know, this new privacy thing. Question, can you use dropout noise? Yeah, you take your data and you just drop half of it. You use your algorithm on top of half of the data, and maybe it becomes robust in some way. Yeah, very, very curious direction. So that's all. Questions? Yes?
So you said that it actually gives a good result both in the worst case and
Yes.
higher decay.
Yes.
Like the potential function-based algorithm, the other algorithms also achieve this type of...
Not the plain Hedge algorithm. The one with the soft min, which is sort of the jewel of this community because it uses these exponential weights. It's related to exponential families. You know, it's related to Bayes rule. This kind of a thing, no, because you have to tune the learning rate, because you have dot loss. But there is fancier algorithms that put some squares up here and do all kinds of other little tricks, and they have batteries of algorithms with different learning rates and put some other algorithms that more complicated. I'm very interesting work, beautiful work, but still more complicated. My answer to this is the following. Okay, this is a long story. Okay, so this is what I'm working on now. Here there's an exponential. The trick has to be that you put here, you replace the exponential by a power distribution. You introduce a temperature into the exponential, not just the learning rate up here, but a temperature into the exponential. Work with that. And then you need another temperature in your loss function. It gets more complicated. You need two temperatures. That's what I'm working on now. And I think that two-temperature model, when the two temperatures diverge, is going to get this automatic tuning for a huge class of problems. But it involves generalizations of the exponential family and all kinds of other techniques. It's quite interesting. Yes?
So you mentioned combinatorial
Yes.
tricks. So how would you define, I mean, the dropouts somehow have to respect the combinatorial structure.
Let's say instead of wanting to learn a single expert, you want to learn a set of experts.
Yeah, I know the definition of combinatorial
Yes.
expert.
Yes.
But how do you define, how do you do the dropout there? Oh,
It's up to you. I don't know.
but
You
it has
could.
to somehow respect the
Yes.
structure. And,
Yes, so you could do for sets of experts. You could still do, maybe the unit rule holds. I think we checked that. I don't remember what we have there. Okay, so in each case, it's a special case, right? You could make up all kinds of problems. The trick that we worked on here is we brought it down to units, and then analyzed that special case. Yeah, please work on it. It's very beautiful. Yes?
So my intuition about Dropout has always been that you're essentially having an implicit ensemble with tied weights. Does that view give an interpretation in this setting?
I don't know. If we go out to a bar and you give me a bunch of beers, I will also talk that way. But I'm in an official position here in front. So I don't know. Don't know. Yes, but follow your intuition. Everybody starts with intuitions, right? And then you follow them, and then you have to prove things. Unfortunately. Unless you have a lot of data and you can make your point with data, then you can also do it. Yes? Somebody said something. Yes?
I'm just wondering, for the matrix hedge, is there anything known if you're okay with slightly worse dependence of regret on n? Like, let's say ln n square root of t, but still you want to get n square runtime per.
I think log n squared Maybe there is some stuff used with done with Gaussian noise. I don't remember all the details there.
So that's-
There could be possible, yes, but there has been a snobbish community and called, they want to get the optimum bound. They would scoff at that. And they wouldn't even write a paper on it. I'm serious. You got to get the optimum bound.
Thanks, Ernst.